Good afternoon, everyone. Let's start. Sorry for the last time. The audio was not clear in the video, right? But I sent another link for another good video. Did you see the good one? Do you hear me? Okay. Now let me share the screen with you. Please write your name and the student ID for attendance, okay? Okay. Remember to write your name and student ID. Let's start. We will continue the mean value theorem. Let me remind you what's the mean value theorem and what's the rules theorem. Let's see. See here, rules theorem tells you that let f be a function that satisfies the following three hypotheses. Okay, let's continue. So let f be a function that satisfies the following three hypotheses. One, f is continuous in the closed interval. Okay. So one, f is continuous in the closed interval a to b. Two, f is differentiable on the open interval a to b. Three, f of a equals f of b. Then there is a number c in ab, the open interval, such that f prime of c equals 0. So this the rules theorem. Okay. Let me remind you the mean value theorem. Mean value theorem, yes, it's here. Mean value theorem, very similar to rules theorem, but it's generalization. See here. The same, one f is continuous in the closed interval ab, two f is differentiable in the open interval ab, then there is a number c in the open interval such that f prime of c equals f of b minus f of a over b minus a. If you want, you can multiply by b minus a both sides, you get fb minus f of a equals f prime c b minus a. Good? And here, what if f of b equals f of a? It becomes the same as rules theorem, right? You get f prime of c equals 0. So this one, mean value theorem, is more general, right? Are you good with this? Do you have questions? Is it good? Okay. You need to participate and pay attention, okay? Because where is it? We will solve the problems now. Let's start with this one. You have the graph of a function g. You have the graph of a function g is shown. Verify that g satisfies the hypotheses of the mean value theorem on the interval closed from 0 to 8. What are the hypotheses of mean value theorem? Let's see. So one, when we have g is continuous that's a problem. So g is continuous on the closed interval 0, 8, right? Is this function continuous? Yes, it's continuous. You don't have open circle, or you don't have jump discontinuity like this, for example. You don't have these things. You don't have like this vertical asymptote. You don't have any problem. So it's continuous, right? Now, part 2, is it differentiable? What do you think?
Yes.
Yes.
Because there is no problem with it, because we don't have corner like this. If we have this, it's not differentiable. Or this, no, just 1 second. Or like this, for example. This is also here not differentiable because it's cusp, right? So we don't have these things here, so it's good. So it's differentiable on the open interval. So g is differentiable. This means what? There is c remember to write your name and student ID, okay? Now, so there is c in the open interval 0, 8 such that what? The derivative at c okay. So f prime of c equals f of not f, here we have g, right? So g prime of c, g of 8 minus g of 0 over 8 minus 0, right? What's the geometric meaning of this? That the slope of the secant, the slope of this line here, right? There is a tangent line that has the same slope, right? If you can see here that you have here tangent that has the same slope, right? Also here, right? So you have two solutions. You have C1. This is part B. Part B tells you estimate the values of C that satisfy the conclusion of the mean value theorem on the interval closed from 0 to 8. So you have C1 equals nearly 2.3 or 5, right? Let's take it 2.5 for example. 2.4. The other solution, C2 here, see here, it's nearly 6.6, right? Are you good with this? If you have questions, please ask me. Let's continue now. Let's solve now the next. Next we have also part C and part. No, 4 is another one. So let's solve part C now. So here again, it's the same graph, but now we are dealing with the interval 2 to 6. So let's make it clear. 2 to 6. It's continuous in the closed interval 2 to 6. It's differentiable in the open interval 2 to 6. So it satisfies the mean value theorem, right? So let's solve it now. Let's estimate the values that satisfy it. So this one. So this is the slope of the secant, right? We want to find tangent that has the same slope, right? It will be nearly here, right? No, not like this. Yes. these are horizontal, right? Meaning that they have the same slope. What's this point nearly? C1 equals nearly 3.6, right? Do you have another solution? Just this solution, right? Because there is no other point having this slope, right? Now let's go to question 4. Draw the graph of a function that is continuous on the closed interval 0 to 8, where f of 0 equals 1 and f of 8 equals 4, and that does not satisfy the conclusion of the mean value theorem on closed 0 to 8. If it does not satisfy the conclusion, what can we do? We need it to be not differentiable, right? So we want function that is continuous but not differentiable. Now we will do that. So not differentiable. Let's see. Here is the graph. Y, x. We want it from 0. Here x value 0. Here 8. X value 8. Here we have at 0 we have the y value is 1, right? Because f of 0 equals 1. Now f of 8 equals 4. So here 4. We want to draw a function that is continuous but not differentiable. We can do like this, right? This is continuous, but here you have cusp. You have corner, right? So here the derivative does not exist here. Do we have the conclusion is not satisfied? I will show you. Here is the slope of the secant. Do we have tangent line that has the same slope? This is different. Here is different. Here we don't have it, it's not differentiable here. So we don't have tangent line that has the same tangent as this one. Are you good with this? Do you have questions? Okay, let's continue. Now, what's next? Not this one. This one. Let's continue. Let's solve this example, example 5. Example 5 is important. Example 5 tells you, suppose that f of 0 equals minus 3 and f prime of x less than or equal to 5 for all values of x. How large can f of 2 possibly be? Okay? We will use mean value theorem, right? But for mean value theorem, you need the function to be continuous. But the example doesn't tell us that the function is continuous. What do you think? Is the function continuous?
Yes.
Why is it continuous? It's not written here that f is continuous. Yes, it's continuous, but do you know why it's continuous from this?
For all values of x.
No, from this one. See here? You have the derivative exists, right? You studied in chapter 2, at the end of chapter 2, that f... Yes.
If a function is differentiable at a point, then it's automatically continuous at the point. At
Yes.
that point, exactly.
Yes, thank you. Yes, exactly. Since we have that this function is differentiable, see here, it tells you f prime of x is equal to 5 for all values of x. So we know that the derivative exists at all points, meaning that it's also continuous, right? So we can use mean value theorem. So here f is continuous on the closed interval and differentiable on the open interval, right? it's more than that. It's continuous for all values, differentiable for all values. So it's clearly satisfy on the closed interval 0 to 2. See here, this 0 is A, 2 is B, okay? Now, if mean value theorem is satisfied, then we have, there is C in the open interval 0 to 2. Remember to write your name and the student ID. Now, let's continue. So, f prime of C equals f of 2 minus f of 0 over 2 minus 0, right? 2 minus 0 is just 2. So, write it 2. Next, what do we do next? Multiply both sides by 2. You get 2 f prime of C equals, what's the value of f of 0? Minus 3, okay? So I will put it. So we have f2 minus 3. Remember, we have minus from the formula, and the value is minus 3. So minus is positive, right? So it's positive 3. Now, I will write it down again, okay? So f of 2 equals what? 2 f prime of C minus 3. Subtract 3 both sides. The question asks you, how large can f of 2 possibly be, right? So how large means, what's the largest possible value of f of 2? So this here, we need to write it less than or equal to, but here we are given that f prime less than or equal to 5, right? So we have this 2, same 2, keep it as it is, then the derivative less than or equal to 5. So times 5 minus 3. 2 times 5 is 10. 10 minus 3 equals 7. So f of 2 less than or equal to 7. Are you good with this? Okay, let's continue. Now we will solve another similar question here, but this time for how small can the value be, okay? But it's the same idea, very similar. Again, do we know whether this function is continuous? Yes, we know, because it's differentiable, right? So let's continue. Where is it? Yes, it's here. So if f1 equals 10 and f prime of x greater than or equal to 2, for x greater than or equal to 1 less than or equal to 4, how small can f of 4 possibly be? So we know that f is continuous. F is continuous on the open interval 1 to 4 because differentiable, right? Remember to write details, okay? Because f is differentiable. Here is closed interval, okay? Remember that for the continuity we need closed, not open. So now what's next? Next there is C. There is C in the open interval 1 4 such that f prime of C equals f of 4. Here 4 is B, okay? And here this is A. So f of 4 minus f of 1 over 4 minus 1. 4 minus 1 is 3, right? So let's write it 3. And f1 is 10. So this equals f4 minus 10 over 3, right? Now multiply both sides by 3. You get 3 f prime of C equals f4 minus 10. Add 10 both sides, you get f of 4 equals 3 f prime of C plus 10, right? We wanted how small can be, right? So what's the smallest value of 4? So we need to write greater than or equal to 3, keep it as it is, 3, but the derivative greater than or equal to 2, right? So 3 times 2 plus 10. Keep 10 as it is. You get 16. Are you good with this? Okay, let's continue. Last time we explained this theorem, right? But let's explain it again because we need it. I mean, today I will solve examples. Last time we didn't have time to solve examples. So we need to explain it again and solve examples. So remember that this theorem is very much important. If f prime of x equals 0 for all x in an interval, open interval, then f is constant on the open interval, okay? Here is the proof. Since it's differentiable, it's also continuous. You assume 2 points, x1, x2 belongs to the open interval with x1 less than x2. Then this closed interval x1, x2 is part of the open interval a to b, right? Because x1 greater than a, x2 less than b, right? So you have 0 equals f prime of c equals fx2 minus fx1 over x2 minus x1. This by the mean value theorem or Rule theorem, okay? No, sorry, not Rule theorem. It's mean value theorem here. Here mean value theorem, because we still don't know whether fx1 equals fx2. We are trying to prove fx1 equals fx2. So here we are using mean value theorem. So mean value theorem. Yes, good. Now, mean value theorem tells us that there is c in the open interval x1, x2 such that f prime of c equals fx2 minus x1 over x2 minus x1. But from the given information here, we have the derivative equals 0, right? So f prime of c equals 0. Now x1 less than x2 means that x1 is not equal to x2, meaning that x1 minus x2 is not 0, right? So multiply both sides by x2 minus x1, you get 0 equals fx2 minus fx1. Add fx1 both sides, you get the result, fx1 equals fx2. And here you assumed x1, x2 arbitrary. So any 2 points, the image is equal. This means the function is constant, right? Here is the proof. You don't need to study the proof. You need just to understand the theorem, okay? That if the derivative is 0 for all x in open interval, then the function is constant on the open interval, okay? The corollary is also very much important. It's the same idea. If f prime equals g prime for all x in open interval, then f minus g is constant on the open interval. That is, f of x equals g of x plus c, where c is a constant. The same idea. You make the function h equals f minus g. Then the derivative of h is 0 because f prime equals g prime. You get f minus g equals c from the last theorem. So f equals g plus c, okay? Now here you have important example. That let's explain this. But before that, do you have questions about the... Are these theorems clear? That if the derivative equals 0 in open interval, then the function is constant in open interval, and the other one, are they clear? Do you have questions about this? Is it good? Okay, let's continue.
Good.
Now, this example here for understanding, okay? Because you need to understand these things. What's the derivative of this function? F prime of x equals 0, right? But is it constant? What do you think? This function is 1 when x greater than 0, minus 1 when x less than 0. What do you think? Is this constant?
Professor, what's the question?
Is this function here constant? This function is 1 if x greater than 0, minus 1 if x less than 0. Is it constant?
No.
No, right? But the derivative equals 0. Does this contradict the theorem? No, it doesn't contradict the theorem, because the theorem tells us that the derivative on open interval. right? But is it here open interval? See here, this set, is it open interval? No, right? Because this set here tells you that x is not 0. What's the meaning of x is not 0? Then minus infinity to 0 open, union 0 to infinity, right? Here this is not open interval, this is two open intervals, so it's not open interval, right? Open interval you need one, just one. But the nice thing here, see here, x greater than 0, it's open interval, right? It's 0 to infinity. So see here, is it constant? Just this part, the first part, is it constant? Yes, right? Same with the other part, right? Which is x less than 0 is also minus infinity to 0, is also open interval, right? So see here that the whole function doesn't satisfy the theorem because it's not open interval. But each part of it satisfies the theorem, right? Is this good?
Yes.
Okay. Do you remember the Pythagorean identity?
Yeah.
Yeah, I will tell you something very nice about it now. Where is it? Yes, it's here. So you have sine squared x plus cosine squared x equals 1, right? Now you may get angry and tell me that what's the relation between calculus and this one, right? But this is very much related. Sine squared x plus cosine squared equals 1. How to prove this? Do you know how to prove sine squared x plus cosine squared x equals 1? There is a proof in trigonometry, right? Or geometry, right? But the proof in geometry and trigonometry is hard. Again, you want to ask me what's the relation of this with calculus? The relation is that the proof in calculus for this is very much easy. You can prove this identity using calculus in a very easy way. Do you see the idea? I will tell you the hint. We will use this. If f prime of x equals 0 on open interval, okay, then f of x is constant, equals c. Do you know how to use this theorem in calculus to prove this identity? What do you think? Do you have idea?
Wait, can you go back to the thing?
Yes.
Do you find the derivative? Do you do it as sine squared x plus cos squared x minus 1 and then find the derivative?
Yes. First, so yes, you are right. So you build the function f of x equals sine squared x plus cosine squared x. You can take just this if you want, or plus 1, as you like. Let's take it without 1. But if you want it with 1, the same idea. So sine squared minus 1, I mean. So sine squared x plus cosine squared x. What's the derivative of this? Two sine x cosine x, right? Plus, using chain rule, right? So 2 cosine x, what's the derivative of cosine x? Minus sine x. What's the result of the derivative? 0, right?
Yes.
Here I didn't tell you what's the open interval, right? You need to ask me about this. I will tell you what to do. Define it on the open interval minus a to a. You may tell me, why didn't you take minus 2 to 2, for example? The reason is that here I want to take the limit. Let a goes to infinity. Then this makes what? That this is true for all numbers, not just open intervals. So in general, if you do it for a, then you can take a goes to infinity, right? And make it to make it true for all values, not just open interval, right? Do you understand this? Now the next step. So the result is sine squared x plus cosine squared x equals constant. How to know the value of this constant? What do you think?
Solve. I don't know actually.
Substitute value, right? For example, x equals 0. Since it's constant, you can substitute value to know the constant, right? Substitute any value and you get the correct constant. For example, substitute x equals 0 because it's the clear value here. Minus a to a. 0 is here, right? What is sine 0? 0, right? So sine 0 is 0 plus cosine squared of 0. Cosine 0 is 1. 1 squared is 1. So 0 plus 1 equals c. So it's 1, right? Do you like this proof? Is it easy?
Yes.
So this proof, the nice about it that it's very easy. The proof from trigonometry is harder. I studied it before, but I always forget it because. But this one in calculus, I studied it a few years ago, and I'm remembering it until now. Okay, so sometimes you can do something in calculus easier than in geometry. Okay. Now we also have similar example here in the file. This identity. Yes, I will take it and we solve it. Okay. You also have this identity now. Now you know the idea, right? You will build the function. You say f of x equals tan inverse of x plus cotangent inverse of x. Then you differentiate. What's the derivative of tan inverse? 1 over 1 plus x squared, right? Plus derivative of this one minus 1 over 1 plus x squared. You get 0, right? So we know that tan inverse x plus cot inverse x equals constant. How to find the value of the constant? For example, put the value x equals 1. If you put x equals 1, you get here pi over 4 plus pi over 4 equals c, and this equals pi over 2, right? Are you good with this?
Yes.
Now you can also prove it without calculus. Now prove that science. We solved this one now. We solved it before the other one. You also have these examples. For example, see here. The graph of a function f is shown. Does f satisfy the hypothesis of the mean value theorem on the interval closed 0 to 5? If so, find a value c that satisfies the conclusion of the mean value theorem on that interval. See here, this function is not differentiable, right? So does not satisfy the mean value theorem on a closed interval 0 to 5. See question 8. Same idea. You have cusp, so it's not differentiable. Let's go down. Graph 6. Yes, it satisfies, right? Because it's continuous and differentiable. So it satisfies the theorem. Let's estimate the value of c. You get f prime of c. See here the values. F of 5. See here of 5 and f of 0. They are equal, right? If they are equal, then the conclusion is that there is c such that f prime of c equals 0, right? Yes, it's satisfied because see here you have horizontal tangent, right? And here at 1 you also have horizontal tangent. So you have solution 1 and 3, right? Yes. Same idea here. You have f is continuous in the closed interval, differentiable in the open interval. When we estimate the value, it's nearly here, right? See here, I will show you more clearly. Let's see. The conclusion is that we have this line, right? We want to find tangent line that has the same slope. See here. It will be nearly here, right? So nearly 3.5 or 3.6. Let's see my estimate before. 3.8. I estimated it last time to be 3.8. So this is the idea. These questions with the graph, I put them for understanding, because you need to understand deeply these things, not just to solve numbers. You need also to understand the theorem. What is the meaning of this theorem? That the slope of the secant line equals the slope of the tangent. Next, let's solve this example. We have more examples, so let's solve some of them. Let's go to practice. So let's solve this one. Now, this for Rule-J theorem. This here is polynomial, right? If it's polynomial, so it's continuous, right? If it's continuous, because it's polynomial. Continuous on the closed interval -2 to 2. 2f, since it's polynomial, it's also differentiable. F is differentiable on the open interval -2 to 2, right? Here it's differentiable on the closed also, because it's polynomial. But let's write it open, okay? And here, in fact, you need to be careful. This will, for example, let me show you x squared. If I write x squared like this, just here and here, okay? This is, for example, -2, here 2, okay? Here it's differentiable open interval, okay? Even if it's polynomial. But if I write the whole graph to infinity, yes, it's continuous at -2 and 2, okay? So it depends on your domain. You need to be careful about this. Here it's, the domain is just this, so it's open here for the differentiable. For Rule-J theorem, we need number 3, right? Which is f of -2 equals -2 cubed, -2 times -2 squared, -4 times -2 plus 2, right? And this equals what? Equals -8, -8, yes, correct, plus 8, plus 2. So -6, right? Let's see f of 2. If f of 2 is also -6, then Rule-J theorem is satisfied. And it will be, because the equation is designed to satisfy the Rule-J theorem, okay? So 8 minus 8 minus 8 plus 2. 8 minus 8 is 0. Minus 8 plus 2 is -6. So let's find now what's the conclusion. Then there is C. You need to solve like this when you solve using rules or mean value theorem. Mean value theorem just the first two, okay? If you are dealing with mean value theorem. For Rule-J theorem, you also need the 3, okay? So let's continue. Then there is C in the open interval -2 to 2, such that f prime of 2, not 2, I mean f prime of C. F prime of C equals 0, right? What's the derivative of this function? The derivative is 3x squared minus 4x minus 4 equals 0, right? I will use now another color. I will use the quadratic formula to find the solution, okay? So what's the quadratic formula? X equals minus b plus or minus the square root of b squared minus 4ac over 2a, right? Are you good with this? I think you are good with this because you know this formula. So let's substitute. Minus b equals minus 4. So minus 4, it becomes positive. So 4 plus or minus square root of b squared minus 4 squared, 16. Minus 4 times 3. So it will be what? It will be square root of 64 over 2 times 3, 6. So it will be 2 over 3 plus or minus 8 over 6. 8 over 6 is 4 over 3, right? So one solution is, I will take up the minus 1. So 2 over 3 minus 4 over 3 minus 2 over 3. The other one 6 over 3, which is 2. Which solution will I take here? Minus 2 over 3 or positive 2? Do you hear me?
Yes.
We want the solution to be in the open interval minus 2 to 2. Which solution will I take? 2 or minus 2 over 3 or both of them? Is 2 in the open interval?
No.
So 2 we don't want 2. Minus 2 over 3 must be in the open interval. Because remember,
Yes.
the theorem tells you that there is C, that in the open interval. If there are more than one solution, you need to check which solution is in the open interval, okay? So here 2 is not. Then the other one must be, even if you don't calculate the value. Good? Now let's solve the question for mean value theorem now. You have another one for rules theorem. Let's solve it to have more examples. So here you have what? Since it's sine x over 2, yes, it's continuous. So f is continuous on the open interval pi over 2 to 3 pi over 2. 2f is differentiable on the open interval. When you solve, you need to solve like this, okay? You need to make your solution very clear. Pi over 2, 3 pi over 2, open interval. Closed and open, they are not the same thing, okay? So for continuous, you write closed. For differentiable, you write open. Now point 3, sine. We need to calculate f pi over 2 and f3 pi over 2. F pi over 2 equals what? Sine pi over 4, right? What is sine pi over 4? 1 over square root of 2, right? Now f3 pi over 2 equals sine 3 pi over 4. 3 pi over 4. Remember, pi over 4 is 45 degrees. This one, 3 pi over 4, 135 degrees. So look at the unit circle. Unit circle means you have radius 1. Okay? So here 45 degrees. Here 135 degrees, right? So 45 degrees here. So here the same values in absolute value, but you need to check the sign. The sign represents the y-axis, right? What's the y-axis? What's the sign here of y-axis? Positive, right? So this one is also 1 over square root of 2. So they are equal. So this tells you that there is C. Please, if you have questions, you can ask me, okay? Because I want you all to understand. So there is C belongs to the open interval pi over 2, 3 pi over 2, such that the derivative f prime of C equals 0. This because rules theorem. And rules theorem equals 0. Now what's the derivative of this? Half cosine x over 2, and substitute C, you get cosine C over 2 equals 0, right? When is this 0? You need C over 2 to equal what? Equals pi over 2, right? Or 3 pi over 2. Multiply both sides by 2. You have C equals pi. And you have what? C equals 3 pi. Which solution will I take here?
Pi.
Just pi.
Okay.
Because 3 pi is not in the open interval. 3 pi is large. Pi is good. Now let's solve. Why does this not contradict rules theorem? Because this function here is not differentiable, okay? this function is continuous, but when you differentiate x to 2 over 3, you will have something in the denominator, right? So you will have 1 over 0 in the derivative. So it's not differentiable, okay? So this is no contradiction to Rolle's theorem. Now let's solve this one, the last one. I think yes, it will be the last one, because it will take nearly 5 minutes to solve this. So verify that the function satisfies the hypotheses of the mean value theorem on the given interval, then find all numbers C that satisfy the conclusion of the mean value theorem. Same idea, this function 1, it's continuous on the closed interval. So continuous on the closed interval minus 2 to 2. 2, it's differentiable, f is differentiable. On the open interval minus 2 to 2. 3 what? No 3 here, because it's mean value theorem, right? Then what's the conclusion of mean value theorem? Then there is what? There is C in the open interval minus 2 to 2. Why do we take it open interval here? Because it's about the derivative, right? So it must be in the open interval. F prime of C equals f of 2 minus f of minus 2 over 2 minus minus 2, which is 2 plus 2, 4, right? Now let's find the value of f of 2 and the value of f minus 2. What is f of 2? F of 2 equals 2 cubed 8 minus 3 times 2 minus 6 plus 2. So it will be 4. Now f of minus 2. F of minus 2 is minus 8 plus 6 plus 2. So equals 0. So here you have f of 2 is 4 minus f of minus 2 is 0. 4 minus 0 over 4, which is 4 over 4 is 1. So the derivative equals 1. What's the derivative of this function? So you have f prime of x equals 3x squared minus 3, right? We want it to be equals 1, right? From here, I want it to be equal to 1. Subtract 1 both sides, you get 3x, or add 3 both sides, not subtract. I mean, you can do any way you want. These things have many ways to solve them. So 3x squared equals 4. Divide both sides by 3. You get x squared equals 4 over 3. I will go here. So x equals plus or minus 2 over square root of 3. Which solution? Here over 3. Square root of 3, okay? Which solution will I take? I need to check them using calculator, right? So we have one of them is positive. Let's take the negative one first. And the other is the positive one. So you have 2 over 3 power 0 point half. Not point half, it's 0.5. So the result is 1.15, right? So one solution is minus 1.15, the other nearly equal, I mean, to be very clear, nearly equals. So are they in the open interval? What do you think? Are these solutions good? Is minus 1.15 and 1.15 in this open interval minus 2 to 2?
Yes.
Yes, so always remember, when you have more than one solution, you need to check the values. Or using understanding. For example, if I have the interval is 4 to 5, for example, and I have two solutions. One of them is minus 3 and one of them 4.5. Which solution will I take? The positive one, right? So this is the idea. When you have more than one solution, you take the correct one. That it's in the open interval. Do you have questions?
No, thank you.
Okay, let's stop here. You can leave if you want. Have a nice day. I will I will take the names before leaving, okay? But you can leave if you want.
Thank you, Professor.
You are welcome.